In this video, we're going to be discussing what an exact ordinary differential equation is. So, before we go into what an exact ordinary differential equation is, let's try to connect the dots with what we've done thus far. So thus far, we've introduced to you what we've introduced several different types of first order ordinary differential equations, right? Where differential equations, you're given a differential equation where you have one derivative of the function, and then likely you'll have the same function, but it won't be in the derivative form. It'll just be, y instead of y prime. And then we discussed four different types of these equations. We talked about linear differential equations, the Bernoulli differential equation, which is an extension of the linear differential equation. We talked about separable differential equations, and then we also talked about the first order homogeneous differential equation, which is an extension of the separable differential equation. And in all those cases, we were given a differential equation, and the goal was to solve it and to find a solution that satisfies that differential equation. But with an exact ordinary differential equation, the problem is a bit different now, because you have to work backwards. And you will see what I'm trying to tell you in a minute. So basically what I'm trying to say is, before, in all these past videos, we've given you a differential equation and you have to provide the solution. You have to solve for the solution. This time we're going to give you some solution, and let's write this down. So this time we're going to give you some solution, given some solution y equals yx of some differential equation, right? Then you're given this solution. The goal is to construct a differential equation where the solution is y. So as you can see now, we're going to try and work backwards, right? And so this is going to bring its own unique challenges. When I first looked at this, it was a bit annoying, but I've tried to boil it down to make sure that it's as simple as it can be. Okay, so this is how it works. A differential equation of the form mxy plus nxy dy dx equals 0 is an exact differential equation. This is the form of an exact differential equation. Now, this exact ordinary differential equation is an exact differential equation if there is a function. Here, I should write here. If there is a function, this is psi. This is the Greek letter psi, x, y, such that your xy is equivalent to the partial derivative of psi with respect to x, and then your n xy is the partial derivative of psi with respect to y. And so therefore the solution y equals yx is given implicitly by psi xy is equal to c, where c is some constant. Okay? And so also note that an exact ODE can also be written in the form of mxy dx plus nxy dy equals 0. Okay, this is an alternate form of exact ordinary differential equation. Okay? All right. So now I'm going to show you how to solve an exact equation. And I'm going to make a flow chart, but I'm not going to complete this flow chart. I'm going to show you a part of it. I'm going to show you what happens before actually I show you the flow chart. I need to tell you about the test for exactness. So the test for exactness is very important. Okay, the procedure for solving an exact equation will always begin with this test. So the test is that the partial derivative of m with respect to y needs to equal the partial derivative of n with respect to x. If this test passes, then all is good. And I'll show you how to solve the exact equation in a second. But if the test fails, then you have to come up with an integration factor, and you have to multiply that integration factor by with the given exact ordinary differential equation to make it exact, and then therefore then the test for exactness will pass, and then you will continue with the procedure. So this is very important. Okay, that's not connecting. That's annoying me. All right, just pretend that connects. Okay, so now let's make that flowchart. So here's your flowchart. Okay, so here's your flowchart for exact equations. So recall that an exact equation has the form m plus n y prime equals 0. Okay, and just know that y is in terms of x. All right, I should put this in a bracket actually. So that's in terms of x. And so now the first thing you do is you do the test for exactness. Okay, so we do the test for exactness. We see if the partial derivative of m with respect to y is equivalent to partial derivative of n with respect to x. Okay, and so if this test passes, if this test passes, then how we talked about the the function psi with respect to x and y. If this test passes, we're always, just know that what we're trying to find is a function for psi, right? So if this test passes, then automatically psi x y will be the integral of m dx plus cy. And I'm writing this cy explicitly here, but if I were to be more clear, just know that m is in terms of x and y, right? So and so is psi. So psi is in terms of x and y, right? And so what's going to happen is when we take the integral right here, in terms of just x, what we're missing out on is the y's, because the y's are being treated as constants or just coefficients of x. And so what we could be missing is some function of y, which we don't account for in this integration. And so as a result, whenever you integrate a function with two or more variables, whatever you're not integrating needs to be in the constant, or it can be in the constant. And the goal is now to find what the hell cy is equivalent to. So in order to get cy, what we need to do is we need to first remember what the definitions of m and x were. So remember that n was the partial derivative of psi with respect to y. So if we can, notice how we solved for psi here. So if we integrate, if we take the derivative of psi with respect to y, then that is also equivalent to n, right? And so then what we can do is we can compare n with what we have here. Or well, we would have to take the derivative of this whole thing with respect to y. And so we would compare and we would cancel some terms out, and then we would get the value of c prime y. And then we would take the integral of c prime y, and that would give us cy, and then we would substitute cy back into here. So let me show you what I'm trying to say. If that was a lot, I apologize. Just watch. Okay, so psi, I'm just right here in this step, I'm gonna take the partial derivative of psi xy with respect to y. And as a result, what I do on one side, I have to do to the other side, right? So then that's gonna mean that I take the partial derivative of the right side with respect to y. So then that means m dx plus cy, like so. And now remember what I just said, that n is the partial derivative of psi with respect to y. So what we've just found is also equivalent to n, right? And so therefore what we can do is we can let me distribute this partial derivative. So psi with respect to y, and then we would have this m dx plus c prime y is equal to n, right? And so therefore what would happen is we would solve for cy. So cy equals n minus this monstrosity, right? And then this and this become their own thing. And so then what we have to do is we have to take the integral with respect to y to find cy, right? And so cy would be some function given by this integral plus some constant. Okay? And so then we found cy. And so then cy is is found, and so then we can plug cy back into psi xy, and that's the whole procedure. And so now that we have that, this is what you need to do if the test passes. If the test fails, which we'll go over after one example, we would have to find an integration factor that makes this equation exact. And then once it's exact, we just follow this same procedure that we just showed. Okay, so let's do this. Let's do an example. All right, so example. Solve 2xy cosine x squared y plus x squared cosine x squared y plus 3y squared y prime equals 0. So please try this on your own, try to solve it, and come back when you've tried. Okay, I'm hoping you've tried it. I'm hoping you've succeeded. Now I'm hoping that you've come back to check your answer. If you didn't figure it out, it's all good. All right, so let's begin. So first thing that we need to identify is that this is indeed written as an exact equation, right? We have m plus n y prime equals 0. This is an exact equation. Okay? And so now what we have to do is we have to do the test for exactness. That's the first thing we do. Test for exactness. Okay? So what is the test for exactness? We do partial derivative of m with respect to y, and we do partial derivative of n with respect to x, right? And so what's going to happen is we're going to take the partial derivative of y with respect to 2xy cosine x squared y is equal to the partial derivative of x with respect to x squared cosine x squared y plus 3y squared, right? And so now let's take the derivative of the left hand side. So this is going to be by the product rule, 2x cosine x squared y, and then this is going to be a negative because we're going to be taking the derivative of cosine. So that's derivative of cosine is always negative sign. So negative 2xy sine x squared y, and then we take the derivative of the inside, that's just x squared. So if I combine the x's, I get x cubed, right? So that's your left hand side, and I should probably align all these because my OCD will drive me crazy if I don't. Okay, so then now we do the same thing on the right hand side. So again, by the product rule, we get 2x cosine x squared y minus x squared sine x squared y, and then this is in terms of x, so then that's 2xy, and then we combine the x's, and then you get 2x cubed y sine x squared y, right? Let me just rewrite that. So therefore, this is an exact equation. Okay? So this is an exact equation, which is great. So therefore we are on this case. We are on this path, right? So now the first thing we got to do is we have to find what psi xy is. Okay? So psi xy, how do we solve this? Well, we already know the equation is exact, which is great. So now first thing we do is we plug in what m is. M is 2xy cosine x squared y, and then dx plus cy. This is rho xy. Okay? And you know what? Let's change the color up, because why not? Let's make it pink. Let's make it hot pink because we can. Okay, so now we have this beautiful hot pink. Anyways, sorry for distracting. Now what we have to do is, I think this looks a lot like a u substitution. So let's do that. So u is equal to x squared y. And so du is going to be, if I take the derivative with respect to x, is going to be 2xy dx, which is perfect. So then we can rewrite this integral as cosine u du plus cy. So then the integral is going to be sine u, and the constant I already took care of on the outside. That's just cy, right? And again, the reason why we have a cy is because m is not only dependent on x, it's also dependent on y. And so we could have some constant. We could have some y being treated as a constant by this integral. So then therefore, we substitute the u back in, and that's going to be sine x squared y plus cy. This is currently the value of psi xy. Okay? And so now we have psi xy, but now we can't just leave this cy here, right? So what we did when we were going through the procedure is cy, in order to get cy, what you have to do is you have to take the partial derivative of psi of what we just found with respect to y, and then that, as we defined up here, is also the same thing as n, right? That's the same thing as n. So then we can equate this to n, and then we can solve for c prime y, and then we can find cy, and then we can plug it back in. Okay, so let's do that. So now we have cy, and so we have cy, so that's great. Or we have to find cy, my bad. So what we have to do is we have to take the partial derivative of psi xy with respect to y, which will give us 2xy cosine x squared y plus c prime y, and this is equivalent to n. Okay, this is equivalent to n. So now recall, n is this monstrosity. N is x squared cosine x squared y plus 3y squared. Oh, wait a minute. I messed up. I messed it up. Hold on. So we're taking the partial derivative with respect to y, right? So you get cosine y, and this would just be x squared, because partial derivative of x squared y with respect to y is just x squared. Okay, yeah, well, that was going to be bad. Okay, I'm happy I caught that now. All right, so then now n is x squared cosine x squared. N is I'm just going to copy this because I'm lazy. N is x squared cosine x squared plus 3y squared. All right, so therefore, as you can see, these two big terms cancel out. So c prime y is 3y squared, and so then you have to take the integral of both sides. So c prime y with respect to y, and then 3y squared with respect to y. So therefore you get cy is y cubed plus some constant. Okay? That's the value of your cy. And that's great, because now all you have to do is you take this, and you put it into here. Okay? Or sorry, not there. That's the u. You put it into here. Right there. And so now, if we put that into there, then you get rho, or sorry, I keep messing that up. You get psi xy sine x squared y plus y cubed plus some constant. This is the value of psi. And what was psi? Psi we defined to be some function, right? Is a function such that it is dependent on m and x, right? It is m and x are dependent on psi, sorry. So therefore we've found the value of psi, which is great. Okay, now let's do another example. But before we do this example, before we do the next example, we're going to talk about the case when the test for exactness fails. So in this example, the test for exactness passed, right? This passed. But a lot of the times the test won't pass. And so then you have to brute force it. You have to come up with some way such that you can guarantee that the equation, the exact equation, is exact. So the way to do that is actually not too bad, and I just have to clear some stuff up. So here. Okay. Let's do procedure. Okay, so if the test fails, and this is real life. This is why I like engineering and not physics, because they always just assume stuff. I'm kidding. Physics is cool. Anyways, okay, so if the test fails, then what you have to do is you have to develop some integration factor. Okay, you have to develop some integration factor. And this integration factor can be one of two things. It can be completely in terms of x, or it can be completely in terms of y. So this is how you develop some integration factor. And I'm going to zoom in. Okay, so you can either have it such that you have px, and px is 1 over n, and then the difference between the partial derivative of n with respect to y minus the partial derivative of n with respect to x. Or it could be qy. And if this does not make sense, just hold on for 1 second. I'll explain myself. Give me a sec. 1 over m, partial derivative. Actually, here, let's move this down because space is limited. Okay. All right. So you have px and you have qx. So then your integration factor, I'm going to use mu. Now recall in the first type of first order ordinary differential equation I showed you, which was linear differential equations, I was using mu t as the integration factor. And this is a similar case, but just know that mu just always means some integration factor. Okay? It can mean different things for different types of differential equations. All right. So you can have mu x or you can have mu y. Now just note before, here, let me just finish this. Px dx e to the q y dy. All right, now this is important. So this is what you have to do. You're either going to have some p such that it is only in terms of x, or you're going to have some q such that it is only in terms of y. Okay, so this is, you have to test both, try both. This is what we will do. Try both, and then one of them will be only in terms of x or only in terms of y, and that's the one you pick. And then from there you put it into mu, into these mu's here, and that's your integration factor. And once you have a mu, once mu is found, multiply both sides of the exact equation by mu. So we have sum m plus n y prime equals 0, right? Then what we do is we multiply both sides by m plus n y, and we just multiply mu with a 0, so that's also 0. And so then what happens is mu m plus mu n y prime equals 0. So then as you can see, these are your new, this is your new m, okay? Your new m, and this is your new n, okay? So you would use this to then put, you would use this, and the test would pass, right? Test for exactness will pass, and you don't even have to test it. Like, I'm not going into the derivation of these formulas, but basically the idea is that px and qy, like the mu will always ensure that the test for exactness passes. But I mean, this is always a good thing to check. So just I guess it wouldn't hurt to check. So the test for exactness will pass, and then you are back to this case where we're going to find psi with these steps, with the new m and the new n. Okay, so let's do that. Let's give you an example. So the example that I'm going to pick is solve 2x squared plus 4xy plus 4x squared minus 2xy y prime equals 0. Like always, please go ahead and try this on your own. Come back when you've tried it. I hope you succeed. Yeah. Okay. I'm hoping that you've tried this. And now we're gonna try and solve this. So, what is m? This is m plus n y prime, right? Now let's try and see what happens if we run the test for exactness, right? So first thing we do is test for exactness. And the test for exactness was the partial derivative of m with respect to y and the partial derivative of n with respect to x. So let's do that. So partial derivative of m, just to be clear, 2x squared 4xy. Let's put this back here. 4xy equals partial derivative of x, 4x squared minus 2xy. So partial derivative of y is going to be 4x equals 8x minus 2y. And therefore, the equation is not exact. So what do we do when it's not exact? Well, we don't just sit and cry like little losers. We solve the damn equation, right? So first thing we have to do is we have to find an integration factor, right? And just to be very clear, the integration factor is mu. It is not p or q, it is mu. All right? So let's find the integration factor. So the integration factor can either be in terms related to p or can be related to q, right? So let's find p of x. Remember, p of x was 1 over n, partial derivative of m with respect to y, minus partial derivative of n with respect to x. Okay? And so our n, actually let's find this difference first. So we already have what partial derivative of m with respect to y is, and we already have what partial derivative of n with respect to x is. So if we were to find this thing here, well, we already know it. This thing is 4x minus 8x minus 2y. Right? So then that means this is minus 4x plus 2y. Minus 4x plus 2y. Excellent. So then what is your n? Your n is 1 over 4x squared minus 2xy, right? And then your difference between the two partial derivatives is minus 4x plus 2y. And this is the value of your px. So then, let's see. Well, we could try bringing the x out in the denominator. So let's try that. So 2y minus 4x. I'm just going to write this as one fraction. I'm going to bring the x out and bring the x out. And then this is 4x minus 2y. And that actually looks very similar, does it not? So if we make this negative and we bring the negative on the outside, that perfectly matches the numerator. So then what we can do is we can just cancel these two out. And so therefore, the value of your px is just 1 minus 1 over x. And this is great. We don't even have to look for qy. I mean, we can, but I don't want to waste your time. But we've already found px, so this is all we need. And px is only in terms of x, and this is the main thing, right? This is only in terms of x. And like, I'm betting you could solve this. I'm betting you qy will not be in terms of y only. Okay? That's just how this works. I'm sure there's like some proof for it, but we're engineers. We don't care about proofs. We care about making it work. So we now know what px is. So that's great. And so what we have to do then is we just find mu x, and mu x is e to the px, integral of px times dx. So then all this will be is integral of minus 1 over x dx, and that's e to the minus ln absolute value of x, right? And then this would be e to the ln 1 over x, and this is just 1 over x in absolute value. Okay? And so there you go. this is, oh, and actually, I forgot to give you an initial condition, but this was supposed to say x is greater than 0. So apologies for that. So if x is greater than 0, then this must mean that we only really account for the right hand side, right? We only account for the positive. So yeah, that's how it works. So we get just 1 over x since x is greater than 0. This was an initial condition. Sorry if that's confusing. I should have been more clear. Okay, wait, sorry. All right, that's the initial condition. And so now we know what our mu x is, which is great. And so now all we have to do is we have to multiply both sides of the exact equation by this integration factor. So now multiply both sides by integration factor mu x. All right, so mu x is 1 over x, and this was your exact equation, and I'm just going to copy this like so. And what we're going to do is we're literally going to multiply by 1 over x on both sides, and that's going to stay 0. And then we distribute the x, so that's going to be 2x plus 4y, and then 4x minus 2y, y prime. And now this guarantees that this will be an exact equation, but for the sake of completeness and trying to be thorough, we will do the test for exactness again. So now we run the test for exactness again. Okay, so let's run this test for exactness again. Recall, test for exactness is delta m, or partial derivative of m with respect to y, partial derivative of n with respect to x. So then this is your new m, this is your new n. Okay, so then actually, yeah, and so this is the new guy, and this is the new guy. These are both new, the new values that we found that we plug into here. So then partial derivative of y with respect to 2x plus 4y, partial derivative of x, 4x minus 2y. So then this will be 4 and this will be 4. And so therefore the test of exactness is now, that now works, which is awesome. So now test for exactness passes. And I'm going to put an exclamation mark because I'm excited. Okay, so now we have that, which is great. Now what we have to do is, this basically boils down to the first example that we did. We are now currently right before this step, before finding the psi. So let's find the psi. Okay, I'm just going to copy this. Okay, let's find the psi. So in order to get the psi, this is our new differential, or this is our reworked, you could call it, or our differential equation that has been reworked to make sure that it is now exact. And I can't choose a color, but okay, I found a color. Green is good. Okay, so now again, this is your m, this is your n, y prime equals 0. So that means we find m dx. So m is 2x plus 4y dx plus cy equals rho xy. So then your dx is x squared plus 4xy plus cy, rho xy, like that. All right. Or I'm so sorry. I keep saying rho, but it's psi. Okay. This guy is psi. So whenever I say rho, I apologize. This is psi. Yeah. Okay. So this is psi. And there you go. So now what we have to do is we have to find cy. So we find cy. How do we find cy? Well, let me remind you. We take the partial derivative of psi that we just found with respect to y. I cannot make this sign. Okay, there you go. So we take this, and that means the x squared goes away, and we're just left with 4x plus c prime y. And recall that partial derivative of rho and partial derivative of y is also n, and n is 4x minus 2y. So 4x plus c prime y equals 4x minus 2y. So the 4x would cancel out. C prime y is minus 2y. We take the integral of c prime y dy minus, or is equal to minus 2y of the integral dy, and then that would be cy is equal to minus y squared plus some constant. Okay? And that is your cy. So then you plug the cy back into your psi, into the function psi. So let's do that. So psi, I switch to a different color. Psi xy, this is going to be brought down here. Psi xy is x squared plus 4xy minus y squared plus some constant. And that is how you solve that equation. And it's kind of nasty. It's kind of a lot of steps. You know, the hardest thing that I found about differential equations was not necessarily solving the equations. That's not too hard. It's just remembering the procedure. Because when I took differential equations, we weren't really given any formula sheets or anything. And it was just, you just had to know it by memory. So yeah, that's just memorizing all these formulas, knowing this flow chart up here that I made by memory, knowing it like the back of your hand. That's the key to solving exact equations. All right, let's do our final example. Okay, so we are given the equation xy dx plus x squared plus y squared dy equals 0 for y is greater than 0. Like always, please go ahead and try this on your own and come back when you've tried it. Okay, I'm hoping you've tried it, and I'm hoping you've succeeded. First thing I'd like to address is this equation is written in an alternate form of an exact ordinary differential equation, right? In the first page, I said right here that this is also an alternate form of exact ODE, but I don't like this form personally. It just doesn't click in my head. I like m plus ny prime. So let's quickly make it into m plus ny prime, right? So m plus ny prime equals 0. So let's divide both sides by dx. So x squared plus y squared equals y prime equals 0. And therefore, this is m, this is n, this is y prime, and this is 0. So now let's do the test for exactness. And I've already provided you with the case if the test fails, so that's like a hint. But just to be thorough, let's do the test for exactness. The test for exactness: partial derivative of m with respect to y, and partial derivative of n with respect to x. So then we take the partial derivative with respect to y, and that gives us x. and we take the partial derivative with respect to n, and that gives us 2x. This is not exact. So this is the case where the test fails, right? We are now going to follow this case where we have to come up with an integration factor. We multiply the given exact equation, and then we multiply that out with the integration factor on both sides, and then only then our equation is exact. And then from there, what we do is we do the procedure that we wrote up here, right? If this test passes, then we solve for psi. So let's do that. Okay. So let's first look at px. Px is going to be 1 over n. So n is x squared plus y squared. And then the difference, this guy, the difference between the two partial derivatives of m and n with respect to y and x respectively, is basically just solved right here. So we can just do that. So partial derivative of m, partial derivative of y minus partial derivative of n, x. So my is x minus nx is 2x. So then this is minus x. So this is minus x. Okay, and then what we can do is we can rewrite this. Px is minus x squared plus y squared. But the problem is this. You see px needs to only be defined in terms of x, but we have this y here, and that's screwing everything up. So we cannot use px, and we cannot use mu x. So then the integration factor must be in terms of y. So let's try y. So let's make it pink because why not? So qy minus 1 over m. M is xy, and the difference between the partial derivatives of m and n with respect to y and x respectively is minus x, right? Minus x, and maybe I should make this in green so it's more apparent. Minus x. And so as you can see, the x's will cancel out and the negatives will cancel out. So qy is just in terms of y, and this works, right? Qy is just 1 over y. Excellent. So then mu y is e to the integral of qy, which is 1 over y dy, and then e to the ln of the absolute value of y. And so there you go. And so then therefore anything e to the ln is just going to yield y, the argument of ln, and that in this case that argument is absolute value of y. So there you go. And then that works, and but know that we were given an initial condition such that y is greater than 0, and so since y is greater than 0, we have to say it is just y. Okay, and therefore mu y is just y. So that means we have to multiply both sides by y. So again, our differential, or our exact equation was xy plus x squared plus y squared, y prime equals 0. So then we have to multiply both sides by y, right? And that's 0. And that's xy squared plus x squared y plus y cubed y prime. There you go. Now this will be exact, but just to be thorough, we're going to run the test for exactness again, and you will see that it is indeed an exact equation. So test for exactness again. Test for I can't write today. Test for exactness again. So test for exactness m, y, n, x. So again, this is m, this is n, this is y prime, this is 0. So m this is xy squared, whoops, and n is x squared y plus y cubed. So then this will be 2xy equals 2xy, and then y would just be considered a constant if you're taking the partial derivative with respect to x. And so therefore, this is exact. Excellent. So that means if we go back to our flow chart, the test has passed, and we are now in this stage where we have to find psi, and psi is the solution, if you will, right? So psi is what we're trying to find. So again, well, I should say our new exact equation is this thing, right? Because we multiplied it by y. So this is our new exact equation, and let me put this on a new page, like so. This is our new mny prime. Okay, these two are both the new adjusted after the integration factor, right? So now what we have to do is we have to take the integral of xy squared dx plus cy, and that's equivalent to psi. And then this would be 1/2 x squared y squared plus cy, and that's rho xy. Yeah. And now we have to take, remember that n was psi with respect to y. So we have to take, we can do the same, and we have to solve for cy, right? So solve, let me get a new color. Let's get blue. Solve for cy, right? So how do we solve for cy? We equate n with the partial derivative of psi xy. Okay, so then that's 1/2 x squared 2y plus cy prime. And as you can see that this half will cancel, and you're left with x squared y plus c prime y, and this is equivalent to n, right? Because we did this here. So n is x squared y plus y cubed. And so these x squareds cancel. Cy prime is just y cubed. So then you have to take the integral of cy prime dy and the integral of y cubed dy, and cy, that's what you get after you integrate, 1/4 y to the 4 plus some constant. Okay? And therefore, now you've just found psi. Psi xy is 1/2 x squared y squared plus 1/4 y to the power of 4 plus some constant. And that is the function. Recall that what was psi? Psi we defined way up here. Psi is a function such that the m and n's are defined by the partial derivatives of psi with respect to x and y respectively. So it's all intertwined, if you will, right? And so therefore we now have psi. So again, all we did this time was we worked backwards, right? And in past videos we were talking about how to solve a differential equation, a first order differential equation, where we were given the differential equation and we were trying to find the solution. This time we did the opposite. We worked backwards. And that's it for this video. Thank you so much for watching. I know this was a long video, but when I first learned exact equations, I got very confused. So I'm just trying to look out for someone else who might be going through the same thing.